Your TA Indiana does not like non-round conduit. I mean, look at his hamster wheel back here. It's a big giant circle. So for these two non-circular conduit problems, we're gonna have to move fast because I think at some point your TA is gonna ditch us and we'll be on our own. Fortunately, the first problem is a super fast FE exam style multiple choice, just plug and chug question. And the second problem is more like a homework or test question, but it's not really that bad. So starting with the FE exam problem, the first thing you're gonna do is just go to the FE exam manual and type in hydraulic diameter. You'll get 3 hits. One is in the fluid mechanics section that's actually connected to hydraulic radius. And the second one you'll see in heat transfer is... And yeah, your TA already ditched us, but stick with me, I got you, we'll get through it. The fluid mechanics section shows that hydraulic radius is cross-sectional area divided by wetted perimeter, and the hydraulic radius is actually the diameter divided by 4, not 2. Again, that seems really weird. Normally, in like every other application of life, we think of diameter is radius times 2, but hydraulic diameter is hydraulic radius times 4. Maybe that's worth getting into in another video, but for this one, just use the equation written in the manual. Hydraulic radius times 4 is hydraulic diameter. So if I divide this shape into 2 rectangles, a 12 by 30 and a 12 by 18, I get 576 inches squared as the cross-sectional area. Since this is an air duct, the entire perimeter will be the wetted perimeter. If this were fluid flowing through it, if the pipe were full, then the entire perimeter would be wetted perimeter. But sometimes fluid problems don't fill the entire pipe. An open channel flow problem might sit only partway through, so there could be scenarios where your wetted perimeter would not be the entire shape. But for this one it is. So just put a dot somewhere on your drawing so you don't forget where you started, and just trace your way around the shape until you get back to the dot and just add up all the lengths. So if I go across 30, down 12, 6, 12, 18, 12, 6, 12, back to where I started. So wraps around gives me a total perimeter 108 inches. So 4 times 576 divided by 108 gives me 21.33 inches. That gives me C, 21 inches for the hydraulic diameter of this non-round pipe, which in the fluid mechanics section appears in the non-circular conduit section, or in heat transfer is called non-circular ducts. And I learned how to solve this problem from your TA Indy, right? He's a cat. He just goes the brute force easy way. Just trace the path that you're given, 108. Let's just move on to the next one. So at least this problem is a rectangle. That's kind of nice. Still non-circular, but rectangle's easier than that weird thing from the last problem. We're given that the material is galvanized iron, and that should start to raise some red flags in the back of your mind. When in your fluid mechanics class have you actually needed to know the material? And it was always when finding friction coefficient to use the Moody Diagram. So that's a little bit of foreshadowing. That's where this problem's going. But the first thing you might be wondering is how do you solve for power loss? What's the power loss equation? And because the most important skill for the FE exam is going to be what search terms do you even plug in to find the equations that you need, right? If you just type in power, you're going to get like a million hits because power appears in almost every engineering course. So what you want to type in is going to be fluid power or pump power. Even though there's no pump in this problem, that'll still get you to the right place, right? And you'll see on this page of the manual a pump power equation, and right above that, a fluid power equation. They're both rho GH times Q, and at first you might think rho GH, think like pressure, like the manometer equation, but that's not what this is here. This H stands for head. In the pump power version, this would be the amount of head that the pump is adding to the system. So then if we're finding power loss in this problem, then in this case, the H stands for head loss, the amount of head that is lost in this problem. And Q is the same thing Q always means in fluid mechanics. It is volumetric flow rate, which not to be confused with Q being heat as you would see it in thermodynamics. So rho GHQ, density times gravity times head loss times volumetric flow rate. Find those 4 things and we finish the problem. Your TA Indy came back just in time to help us out finding G, which is of course the easiest term. It's just gravity, 9.81 meters per second squared, gravitational acceleration. Thanks a lot, Indy. So since we're given atmospheric pressure, we can just go back to the tables in the back of your textbook, find the right temperature row, and grab the density value. Again, while you're there, just to save a little bit of time, might as well go ahead and write down viscosity as well. I'll go ahead and write down the new value, right? Looks like a cursive V, which even though I already have density, I guess I could grab the other one anyway. But when I calculate Reynolds number, I always like using the little script V new. Because when calculating the Reynolds number, that means you won't have to use density again, even though I already used it once. Oh, Q, we were given that in the problem statement. So yeah, let's just go ahead and write down that was 6. Awesome, hey, just like that, we're 3/4 of the way done. We're almost there. So to find friction head loss, that's the Darcy Weisbach equation. Head loss is the friction coefficient, which we're gonna have to grab from the Moody table. We got a length divided by a distance, and then also a velocity squared over 2g. So for the non-round conduit, that diameter in the bottom is actually gonna be this hydraulic diameter. That's the whole reason we found it, was to plug into this friction equation. It's sort of the equivalent diameter. We went from just needing to find one thing to now we're trying to find 5 things. We're going in the wrong direction, but let's see what we got. All right, length was given right off the bat, 100 meters, so 1 down. Velocity, we can get that pretty easily as well. We were given volumetric flow rate, and if you take volumetric flow rate divided by cross-sectional area, that gets you to velocity. So we got 33.33 meters per second. We plug in there and square it because velocity squared. Okay, gravity. Indy already helped us out with that one. 9.81 meters per second squared, making progress. Hydraulic diameter, back to the main point of this video. 4 times cross-sectional area divided by wetted perimeter. So the area, 1.2 times 0.15, because I want to be working in meters instead of centimeters, right? Always the same thing, meters, kilograms, newtons, try to work in those base units. That way units will cancel out a little bit easier. Wetted perimeter for this shape, we've got 2 sides that are 1.2, 2 sides that are 0.15. So wetted perimeter of 2.7 meters. So do the division, 0.2667 meters hydraulic diameter. So hydraulic diameter, nothing to be scared of. That really is the easy part of these problems. So we're back to just needing one term. Just need to find friction coefficient and plug that in, and then we'll be able to get head loss, and then we'll be done. But using the Moody diagram to find friction coefficient, we're gonna need 2 other things, the Reynolds number, and then also that sort of smoothness thing, right? That takes into account what material it's made out of. Reynolds number, velocity times diameter divided by viscosity. I already looked up viscosity before. We already got the hydraulic diameter. We got velocity. Plug all these in. Reynolds number of 604,000, or I'll call that 6.0 times 10 to the 5th. You want to know the 10 to the power because that's what you're going to actually look at on the Reynolds diagram, right? There's a lot of powers of 10 on there. In the FE reference manual, hit Control F, type in Moody to look for the Moody chart, and you get pulled up, you see the figure, and you also see a list of materials with their roughness coefficients. So galvanized iron provides a whole range of values. I'll just pick the number right in the middle because I have no good reason to expect it to be unusually smooth or rough. Just pick the number in the middle. And so relative roughness is not just this value epsilon, right? It's epsilon divided by diameter. So I'm using that hydraulic diameter again. Again, anywhere you would use the regular diameter for a non-circular conduit, non-circular duct, you just use hydraulic diameter instead. 0.00056. Looking over at the right-hand side of this chart, there's always going to be a ton of zeros you're going to have to keep track of for these. So this 0.00056 looks like it's right around this red line on the Moody diagram. And my Reynolds number was a 10 to the 5th. And so between 10 to the 5th and 10 to the 6th, I'm going over to the 6. So I was 6 times 10 to the 5th. So I trace that up with an orange line. So my red line sort of follows the bend of the curve. I try to keep the same distance between it and the black line right above it. And where it crosses the orange line, that's the point I'm looking for. So I trace that straight over to the left-hand edge. It looks a little bit below 0.018, so I'll maybe call that 0.0178. But you're kind of eyeballing it. Depends on how accurate you draw your lines. Again, do your best. It's kind of eyeballing it. Just get close. Get as close as you can. So I bring that 0.0178 back to my head loss, Darcy Weisbach equation, plug in all the numbers, cancel out the units, get head loss 377.9 meters, and I can bring that back around now to the power loss equation, where I've got density, gravity, this new head loss number, and my volumetric flow rate. And because all of my units are regular, like newtons, kilograms, seconds, my 27,000 answer is going to be in watts. But since that's a really big number, maybe I actually want to write that as power loss equals 27.2 kilowatts. So final answer, boxed in red, power loss, 27.2 kilowatts. Your TA Indiana has been sleeping the whole time and not helping us out at all, except for giving us the gravity 9.81, which we already knew anyway. But that's all right. He's cute and adorable, and I still love him. So if you are very thankful for your TA Indiana's help on this, maybe hit the thumbs up for this video. And if you actually learned something, maybe consider emailing it to one of your classmates if you think it would help them out as well. But if you're really feeling the rhythm right now and you want to keep going with more fluid mechanics videos, maybe more friction coefficient, Moody diagram type videos, then go ahead and click on the one linked on the screen right now.